Okay, so we're on to chapter 8. We're almost done. Can you believe it? So now we're going to be discussing oblique triangles. So before we're talking about only right triangles, so what an oblique triangle is it's simply a triangle that's not right, or a triangle without a right angle. Okay, so I have a couple examples here. I have a 30 degree, and 120 degree angle. And I also have a 20 degree, 137, and 23 degree angle. So since none of these angles are exclusively 90 degrees, then they are oblique triangles. Okay, so now we're going to be learning how to solve these triangles. Okay, so we can solve these triangles if we're given any of the information below. Right, so if we're given all sides but no angles, then we can solve for the interior angles. This is called a side-side-side triangle, or an SSS. Right, now if we're given two sides and the angle between them, we can also solve for the remaining two angles and remaining side. This is called a side-angle-side triangle. Okay, so that's the two angles, or I'm sorry, the two sides and the angle between them, so side, angle, side. Alright, so case 3 is when we get quote-unquote all angles on one side. Right, that's known as an ASA or an AAS. Right, so that's angle side angle or angle angle side. Okay, the reason I say all angles on one side is because a triangle has 180 degrees total. So if we know this angle and we know this angle, then we know that this angle here would be 180 degrees minus the two other angles. So really, even though they only give us two angles, they're really giving us all three without knowing it. Okay, so it's all three angles on one side, an ASA or an AAS. Alright, last but not least is one angle and the side opposite and adjacent. Okay, so that's known as an SSA. So that's angle side side or side side angle. Okay, so we're given the angle, the side opposite, and then one other side. Notice that both of these sides are adjacent because neither of them are the hypotenuse. So I could have easily had circled this side as well. Doesn't matter as long as we have one of the remaining sides. Alright, now let's get on to talking about law of sines and cosines. Right? So case 1 and 2, those are going to be working with law of cosines. We're going to be learning about that a little bit later in 8.2. Okay, so these two up here are going to be using law of cosines. Case 3 and 4, that's going to be using law of sines. That's what we're going to learn about today. So that's these two cases down here. And the reason this case has a star by it is we're going to see that it's very special. Alright, as promised, case 4. Side-side angle. As I said, this is an angle, the side opposite and another side. So, for example, let's say that we were given side A, B, and the angle alpha. Okay, so that would be considered a side-side angle because A is opposite alpha, and then we're given the other side. Also C, B, and angle gamma. C is opposite gamma, and then we're given another side B. So that would also be an SSA. And notice here that I have the same sides, and I'm given the angle beta, and I'm still in an SSA triangle because B is opposite of beta. Alright, now with case 4, we have three possibilities. We can have no triangle. Now in this example here, we were given the angle 50 degrees, and we were given that the side opposite that was 5, and then one of the side lengths next to it was 14. Now notice that the side length 5 is too short to ever connect down to the base while still preserving this 50-degree angle. Okay, so that would be a case of no triangle. Right. Case 2 is when we have one triangle. That's where we can only form one triangle. It's kind of boring. We'll get to that a little bit later. Okay. And then we have this awesome case, my favorite, of when we can possibly have two triangles. So an example is, say we're given that beta is 45 degrees, so this is our angle here, and side length B, so it would be the side opposite of beta, is 6, and C, one of the sides adjacent, is 8. Then we have two possibilities. We can either let B rest out here, let our 6 leg rest out here, or we can swing it in and let it rest right here. Okay, I'm actually going to have a demonstration in the next video that's really going to make this a little bit more clear how we can swing this in and have one triangle, swing it out and have another triangle. Alright, let's get on to what the law of sines is. Okay, so let's say we have an oblique triangle with standard labeling, and I'm just going to label this dotted line here H. So that's going to be the height of my triangle. Okay, and it's going to create a right angle here. That right angle is going to be on both sides. Now I know if I'm in a right triangle, I know that sine of alpha equals my side opposite, that would be H, over B. Okay, and let's go ahead and let's just solve for H. So if I solve for H, then that's going to give me B sine alpha equals H. Alright, let's do the same thing for this angle over here. So we know that sine of beta, since we're in a right triangle on the inside, is going to be side opposite, that's H again, over C. Okay, so that's H over C. Oh, I mislabeled this. So that's not alpha, that's actually gamma. My apologies. So if I solve for H here again, then I'm going to get C times sine of beta equals H. Now since these two are equal, I'm going to set them equal to each other. And I'm going to get B sine gamma equals C sine of beta. And I'm going to divide both sides by BC. Right, now when I do that, notice that these B's cancel out on this side, and the C's cancel out on this side. Okay, and then what I'm left with is that I have sine of gamma divided by C is equal to sine of beta over B. Okay, and if I had changed my labeling, then that also means that sine of alpha over A is also equal to these three. Alright, so what I've done is I've created a system of ratios to help me solve for an unknown value. Okay. Alright, so let's go ahead and do an example. So for example, if I had, let's say that gamma equaled 55 degrees, and let's say that C equaled 7, and let's say that B equaled 5, then I could solve for beta, because then I would have that sine of 55 degrees over 7 equals sine of beta over 5. Okay, and then I would just multiply both sides by 5, then take sine inverse to solve for beta, if possible. Remember, I still have the possibility of having no triangle. Okay, so this is our law of sines rule that we're going to be using. This can also be written as C over sine gamma equals B over sine beta equals A over sine alpha. Right, these are the same rules, just a different way of writing them. Notice that I didn't use all three when I was doing this one down here, so you only need to use one equality sign. So you can either set sine gamma over C equal to sine alpha over A, or sine beta over B equal to sine gamma over C, or to sine alpha over A, it doesn't matter. Also quickly note that this form is used when finding angles, and this form is used when you're finding sides. Okay? They're the same formulas, we just use one instead of the other. The math is a little bit easier, you don't have to flip anything around. Okay, so make sure to write these down and keep those handy as we go through examples. Oh look, we have an example right here. Alright, so say that we're given that A equals 4,800 feet, beta equals 48 degrees, and gamma equals 75 degrees. Okay, now it might not be obvious what we're going to be doing since we have alpha, beta, and A, but because we know these two angles, we can solve for alpha. So if we do that, we get that alpha is 57 degrees. Right, now I want to solve for C, and I want to solve for side length B. So plugging those into my formula, I'm going to get that 4,800 over sine of 57 degrees is going to equal B over sine of 48 degrees. Alright, so I'm going to multiply both sides by sine of 48. I'm going to get 4,800 times sine of 48 degrees over sine of 57 degrees equals B. Okay, let's plug in our calculator and see what that's going to give us. So we have 4,800 times sine of 48 divided by sine of 57. Okay, so that means that B is going to be 4253.27. Okay, now let's go ahead and solve for side length C. So if we're solving for side length C, it might seem like a good idea to use the Pythagorean theorem. Remember, the Pythagorean theorem only works if we're in a right triangle. Okay, so we can't use the Pythagorean theorem yet unless we're using a right triangle. Alright, so make a note of that. So Pythag a squared plus b squared equals c squared only works on right triangles. Alright, now to solve for C, we're going to do the same thing that we did to solve for B. Okay, so we're going to go 4,800 over sine of 57 degrees equals C over, now we're going to be using gamma, sine of 75 degrees. Okay, if we multiply both sides by sine of 75, that will give us C. So let's go ahead and do that. Okay, enter that into your calculator. And you should get that C equals 5528.33. Alright, now let's see if we look at example where we have beta equals 85, gamma equals 40, and b equals 26. Okay, again, we can solve for alpha by taking 180 minus beta minus gamma, and we're going to get that that is 55 degrees. Alright, so let's go ahead and solve for a first. So we're going to have 26 over sine of 85 equals a over sine of 55. Right, from that we're going to have that 26 times, remember, multiply both sides by sine of 55, over sine of 85 equals A. Plug that into our calculator. Okay, we get that A is 21.38. Let's go ahead and round that up. Alright, so now we have A. Now we need to find our value for C. Now remember, we can't use Pythagorean theorem because that only works with right triangles. So we're just going to be doing what we did here before. So it's going to be 26 over sine 85 equals C for sine of 40. Okay, so that's going to be 26 times sine of 40 over sine of 85 equals C. If we plug that into our calculator, we will get that equals 16.78. Okay, so I got 16.78 by rounding that up. Alright, next we're going to be moving on to our ambiguous case in the next video, and that concludes our non-ambiguous cases.